Hello everyone! In this video, I'm going to give you a brief introduction into complex analysis. Complex analysis provides powerful methods for solving real integrals, series, and much more. The goal of this video is to introduce main concepts, theorems, and methods of complex analysis. Using these methods, we are going to evaluate the two following integrals, which would be pretty challenging to solve using standard methods of real analysis. In order to understand everything in this video, I'm going to assume that you are familiar with standard limits, derivatives, ideally even partial derivatives, integrals on real line, and basic manipulation and properties of complex numbers. Let's start with introducing a complex function. A complex function f is a function that takes a complex number z and assigns to it a unique complex number f of z. Since f of z is a complex number that is dependent on z, that is, x and y, it can be decomposed into its real and imaginary part, which are both real functions of x and y. We can therefore say that a function f of z can be written as u plus I times v, where u and v are both functions of two real variables x and y. Every complex number is given by its corresponding pair of real numbers. A complex differentiable function is called an analytic function. We define the derivative of a complex function in a similar way we define the derivative of a real function with one small difference. In order for a real function to have a derivative at a point, the limit of the ratio must be the same no matter if we approach the point from the left or the right. For a complex function to be analytic, the limit of the ratio must be the same no matter the direction we approach the point from. There are infinitely many directions from which we can approach a complex number. An analytic function satisfies Cauchy-Riemann equations, which come from approaching a given point from different directions. Suppose we have an analytic function f that is differentiable at a point z. We first approach z along the horizontal line, that is, changing only its x value. If we write f as u plus I times v, plug in and manipulate the terms, we end up with f prime z is equal to partial u partial x plus I times partial v partial x. We then approach z along the vertical line, changing only its y value. If we again write f as u plus I times v and manipulate the terms, we end up with the following expression. In the first term, we multiply top and bottom by I and find that f prime z is equal to partial v partial y plus I times negative partial u partial y. Because the two expressions are equal, their real parts and imaginary parts must be equal. We call these equations the Cauchy-Riemann equations, and they provide a necessary and sufficient condition for a function to be analytic. If two functions are analytic, their sum and product are analytic, along with their ratio as long as the denominator is not zero. Let's look at an example. Consider a complex function z squared. If we write z as x plus I times y and do some basic algebra, we find the corresponding functions u and v. If we then take the partial derivatives, we see that they indeed satisfy the Cauchy-Riemann equations. Therefore, z squared is an analytic function. We now move on to curves. A curve is a pair of all points given by their x and y coordinates. These coordinates are functions of t. We say that a curve gamma is parameterized by x and y with respect to t. Every curve given by its two real coordinates has a corresponding complex curve. Here we can see the power of complex numbers, since we can represent a pair of real numbers by only one complex number. An example of a curve is a circle in counterclockwise direction with radius r. If we parameterize the circle by its inner angle theta, we can deduce that its x-coordinate is given by r cosine theta and its y-coordinate by r sine theta. For a closed circle, the angle theta goes from 0 to 2 pi. Its corresponding complex circle is given by r cosine theta plus ir sine theta. By the famous Euler formula, this is equal to r e to the I theta. This can be shown by observing that cosine theta plus I sine theta satisfies this differential equation. If we solve this equation by usual methods, we observe that indeed cosine theta plus I sine theta is equal to e to the I theta. However, all of our calculations could be done by using only the expression cosine theta plus I sine theta. We move on to line integrals. If we are given a curve gamma parameterized by x and y with t going from alpha to beta, and we are also given two functions p of x and y and q of x and y on gamma, then the line integral along gamma of p dx plus q dy is defined by the following equation. If a curve encloses a region R, we call this curve partial R or simply the boundary of R. If p and q are functions on R and partial R, then Green's theorem states that the line integral along partial R of p dx plus q dy is equal to the integral over the whole region R of partial q partial x minus partial p partial y dx dy. We will now prove Green's theorem. We first prove the theorem for a rectangle bounded by x1, x2, y1 and y2. To integrate a function f of x and y over R means to take the integral of an integral of f of x and y with corresponding boundaries. The line integral along partial R is equal to the sum of line integrals along all the sides of R. On gamma 1, x goes from x1 to x2 and y is y1. The derivative of x is then equal to 1 and dy is equal to 0, since y does not change on gamma 1. The line integral along gamma 1 of p dx plus q dy is therefore equal to the integral from x1 to x2 of p of x and y1 dx. Along gamma 2 we have x constant and y going from y1 to y2. We calculate the same way integrals along gamma 3 and gamma 4. Their sum is equal to the following. Using the fundamental theorem of calculus, we finally get that Green's theorem holds for a rectangle. To prove Green's theorem for an arbitrary region, we fill this region with small rectangles. On each of these rectangles, Green's theorem holds. The sum of integrals over all the rectangles is equal to the integral over the whole region if these rectangles are small enough. The line integrals along neighboring sides of these rectangles cancel out, since they go in opposite directions. We therefore end up only with the line integral along the boundary of our region, and Green's theorem therefore holds for an arbitrary nice enough region. We move on to integrals in a complex plane. Let us have a curve z that encloses a region or a domain D. Let a function f of z be analytic on D and partial D. We define the line integral over the boundary of D by the following equation. We now write z is equal to x plus I times y and f is equal to u plus I times v. We manipulate the integrand into the following expression. We can now apply Green's theorem with u being equal to p and minus v being equal to q in the first integrand and v being equal to p and u equal to q in the second integrand. Since f is analytic, we can use the Cauchy-Riemann equations to observe the following. If f is analytic everywhere on a domain D and its boundary, the integral along this boundary is equal to 0. This is one of the most important theorems of complex analysis and is called the Cauchy's theorem. We will use this theorem to evaluate the integrals mentioned in the beginning of the video. Let's have a function e to the iz over z, which is analytic everywhere in the complex plane, with the exception of z being equal to 0. We will integrate this function along a quarter puncture disk with outer radius r and inner radius epsilon. We will then let epsilon go to 0 and r go to infinity. The line integral over this curve is equal to 0 by Cauchy's theorem. On gamma 1 we have z being equal to x and dz being equal to dx. X is going from epsilon to r. On gamma 2 we have z equal to r e to the I theta, dz equal to I r e to the I theta d theta, where theta goes from 0 to pi over 2. On gamma 3, z is equal to I times x, dz equal to I dx, and x goes from r to epsilon. On gamma 4, z equals epsilon e to the I theta, dz equal to I epsilon e to the I theta d theta, and theta going from pi over 2 to 0. By plugging all this in and manipulating, we get the following equality. If we let r go to infinity and epsilon go to 0, then the second integrand is equal to -1. To see this, plug in epsilon equals 0 and use Euler's identity to expand the exponent. Since the terms in the brackets are bounded by -1 and 1, and e to the minus r cosine theta goes to 0 as r goes to infinity, the integrand really is equal to -1. Therefore, if we let epsilon go to 0 and r to infinity, and equate the real and imaginary parts, we get the two interesting integrals. Let's now consider a case where the function in question is not analytic everywhere inside of D. Let z0 be inside of D, and let f of z be analytic everywhere in D. Say we have to evaluate the integral along partial D of f over z minus z0, which is not analytic for z0, and therefore Cauchy's theorem doesn't apply. Let us define a new counter. We follow partial D normally, and after some time take a straight path to z0. We make a circle around z0 in clockwise direction with radius epsilon, and then follow a straight line back to partial D. We have now defined a new counter that does not enclose z0, and so Cauchy's theorem applies. If the two straight paths lie on each other, the integrals along them cancel out, and we are left with the integral over partial D and gamma. We parameterize gamma by z being equal to z0 plus epsilon e to the minus I theta. The exponent is negative because we are going in a clockwise direction. dz is equal to minus I epsilon e to the minus I theta d theta, and theta goes from 0 to 2 pi. If we cancel out in the integrand and let epsilon go to 0, we get the following Cauchy's formula. We now consider a following problem. We integrate the function e to the I az over z squared plus b squared along a semicircle with radius r. The function in question has a singularity at a point z equal to ib, and can be written in form where we can easily apply Cauchy's formula to end up with the following. The other singularity in z equal to minus ib is irrelevant since it is outside of D. We now compute the integral along the boundary of D. On gamma 1 we have z equal to x, dz equal to dx, and x going from minus r to r. On gamma 2 we have z equal to r e to the I theta, dz equal to I r e to the I theta d theta, where theta goes from 0 to pi. Plugging all this in leads to the following scary looking integral. We are interested in the limit as r goes to infinity. We do some algebra to manipulate the integrand and end up with the following expression. With little more effort, we can see that this expression goes to 0 as r goes to infinity. By breaking up our original function into its real and imaginary components, we get the two integrals. The first one is the one mentioned in the beginning of the video, and the second one is trivial since its integrand is an odd function. This concludes our video. If you have any questions about this topic, please leave me a comment. That's it from me for today. Thanks for watching.